Start
data
over.
treatment here. And we've, together with a group of other engineers too, developed some very exciting microwave imaging technology. We've developed our own integrated circuits using gallium nitride. Here's one of these integrated circuits, which is a complete radar on a single chip. It produces a 4-volt pulse, electrical pulse, that's about 30 picoseconds wide, sends it out to this antenna right there, which is in contact with the skin. The return signal is then measured again in the same chip with a sampler, a microwave sampler. And we have a patented sampler and pulsar architecture that's extremely low cost and very small and very low noise. And we basically put out 100 million pulses a second, approximately, with these antennas, look at the resulting echoes, and we can see what we can see the effects of vascular activity in the brain. Like you see arteries that are pulsating, they're expanding and contracting. The wall motion of those arteries shows up as motion that we can see at different depths. And also we believe we're seeing evidence of functional activity in the brain, which we believe has never been done before, except in small animals. It's a study by X.P. Lee in rats where they were able to measure with microwaves. So we think we're the first to do it in humans. And the first human to do it is myself. And we have this little helmet here. You can see it has an array of antennas in the helmet. Each of those antennas is on a flexible PC board, so you can press in on it. It's nice and flexible. It's going to conform to my scalp, my head. And we take these antennas, and they actually go then with the flex cables into this, more of these boards right here that we saw. You can see right there. These go into a back-end data acquisition board. It's an UltraView A to D board that's customized to do extremely deep averaging. In other words, it can do zero dead time average. It can look at these return echoes over and over and take one after another and average them on top of each other with no wasted time. So we've done everything that we feel we can do to increase signal to noise. So we get these very faint signals from the activity in the brain. And we then take this helmet and we can just put it on my head. I gotta take my glasses off on this one, but the next helmet's gonna not cover my eyes quite as much and be able to keep them on. And then I'm gonna just fasten this in the back, which is a little bit of a nuisance. And we want to thank Jack Gallant's group at UC Berkeley for making these helmets for us. And anyway, basically I'm wearing this helmet right now, and I could go about doing what I want to do. I could be driving a car. Maybe if we get the helmet a little bit better, I could be jogging like I like to do. And this helmet could be battery powered, and it could be connected to a single Ethernet jack that we can later have a wireless Ethernet. And I could be doing something, and people all over the world could look at my vascular and neural activity once we develop this. We have a long way to go. We have no spatial resolution. This is a problem that people have been trying to solve for decades in microwave imaging. We may not solve it, but we think we have better hardware and more miniaturized hardware that we can pack antennas much more closely than ever has been done before. So we think we have a shot at re-attacking that problem and trying to get a functional imager that's portable, unlike a 7-ton fMRI that a person cannot use for operational environments. So that's the problem we face. It's difficult. Can't be sure if we'll make something successful on that, but we're trying very hard and looking to get partners that can help collaborate with us in this. Thank you.